Hello and welcome to this section of the Physics 3 tutor. In this section we're going to kind of apply what we've learned in the last few sections on finding out what the force is on a wire that's carrying an electric current in a magnetic field, and we're going to apply that to something that every one of you has experience with, and that is basically the concept of an electric motor. If you slice open an electric motor, or if you go on the web and look at pictures of the inside of a motor, you're pretty much going to find two things in every single electric motor that you see. You're going to find permanent magnets inside that motor, and you're also going to find coils of wire. So the electricity goes into that motor, current circulates in the wires in there and the coils in there, and there's also a magnet, permanent magnets fixed inside the housing of all of these motors, and somehow through the magic of science and engineering this causes the motor to turn. So all we know from the outside is we put electricity in and then a shaft begins to spin. And that's pretty much how every electric motor works. What we're going to do in this section is kind of pick apart that and learn how coils of wire can cause, forces to arise that are going to basically want to cause these things to rotate. So it's basically the fundamental theory behind how a basic motor works. And it's not too hard to understand that it might actually work out this way, because we've already established that if you have a magnetic field and you have a wire in a field and you run an electric current through that wire, that a force will push that wire in a certain direction. And we also did an example before where we had a curved piece of wire and we saw what the force was here. What we want to do here is figure out, is there a way to take a coil or a loop of wire, so instead of just a straight wire, it's actually going to be some sort of loop that comes back around. What will happen if we put a loop, some kind of a loop that's carrying electric current inside the field? And I'll just tell you the punchline. The punchline is that loop is going to want to rotate. It's not going to want to move left or right or up or down. It's going to want to actually rotate about some axis. And if you construct it correctly, and if you wind a bunch of loops, which is a coil, on top of one another, right, a bunch of little turns, then you will get the thing that wants to rotate very, very rapidly. That's what we call a motor. So that's the punchline, so what we want to do is sort of investigate that and figure out how it works. So the first problem, so to speak, is we're going to actually derive the torque on a current loop. I could just give it to you, but it's so important and it's such a great application of how we can use these things in real life that I think it's important for us to actually just sort of dive into it. So let me first begin by drawing, or trying to draw, a basic loop on the board. All right, so here's going to be my first stab at drawing one of these things, and you have to use your imagination a little bit, because I'm trying to draw it sort of three-dimensionally, because these coils are basically three-dimensional animals. They're going to rotate, so you have to give it some depth to kind of understand what you're looking at. What you're looking at here is a flat coil, or I shouldn't say a coil, a single loop of wire. You can kind of imagine it being this rectangular thing. It's in the shape of like this rectangular piece of paper like this, and it's kind of, it's sitting sort of obliquely here, and you can sort of see that there. And we'll just do a quick, some quick labeling, because we'll use these labels later. We'll call this side A. We'll call this also side A. What I mean by side A is this has a length A and this has a length A. This guy we'll say has a length B. This guy has a length B, so we know it's rectangular. One thing we're also going to draw, and we'll see why. Let me take this off for just a second. We'll see why here in just a second. We're going to draw a vector from the center of this loop kind of up like this, and this is 90 degrees. This is what we're going to call the normal vector. We'll see why it's useful later. It's going to kind of bog us down if I try to get into it right now, but it's basically just a vector. This is a rectangular thing, right? I can define a vector that comes straight out perpendicular, so no matter how the coil is oriented, no matter how our coil is oriented, this normal vector always comes out perpendicular to it. The reason we do that is because later on, once we get to the end of the section, I'll show you that it's actually easier to keep track of the direction of this normal vector in terms of how our coil is pointed. So we want to know which way it's pointed. We just kind of look at that normal arrow. That's really the only reason we do that. Okay, now there's obviously got to be some current flow here. If there's no current flow in a coil, right, then just like there's no current flow in a wire, there's no force on it from a magnetic field. If there's no current flow in a coil, then there's not going to be anything trying to turn it round and round as well. So that's why we need to draw some current. So let's say that there's some current going this way. It's got a value I. And just to kind of keep it consistent, I'll just sort of remind you the current goes down this direction, the current goes over this direction, the current goes, you know, up that direction. So it's just circulating clockwise like this, round and round and round. Of course, in real life, there's needs to be a circuit with a battery or some wires connected to the coil and all that. We're not talking about how to build a motor. We're just trying to get the theory of it. So just pretend you have a coil, or I should say a single loop of wire in this case. Current's going round and round. All right. Now, if we just have this coil sitting out in space somewhere, totally away from everything, then the current's going to go round and round and nothing's going to happen. Only something interesting happens when you take this coil and you place it inside of a magnetic field. And what we're going to do is look at the forces that occur on all four of these sides, the same forces that were occurring in the wires that we were looking at in the last section, and we're going to see what's happening, because when you think about it, there's really a straight wire here of length, you know, A, we're calling it. There's a straight length of wire on this edge, we're calling it length A. There's a straight length of wire here, which is B, and a straight length of wire here, which is B. So since in the last section we already talked about what the force is on a wire in a magnetic field, now we have four wires. So we want to analyze what that is. So it's a direct extension of what we did already before. Okay, so to proceed, what I want to do is, you know, this is sort of like the oblique view. And what I'm going to do is kind of draw like a little divider line here, like this. And over here, I'm going to draw sort of like a side view of this coil. So now we're going to place this coil in a magnetic field. This is a magnetic field here. And it's just uniform, and it's pointed in this case for illustration purposes to the right. Okay? And it's uniform, it's everywhere. It's it goes this direction, it goes, you know, all through empty space. No matter where I measure it, it's pointed over to the right. Okay, so we're just going to claim that it's perfectly oriented like that. Now, inside of this magnetic field, we take this coil and we put it in here. So I'm basically going to kind of superimpose it, but again, I'm drawing it not obliquely like this. I'm going to draw it edge on. So basically, your coil is going to look something like this. All right. So what we're going to have is, if you can kind of think of what something like that on the side might look like, this is the coil basically like this. Now again, you have to use your imagination a little bit. Here's the three-dimensional representation of the coil. It's looking like this. So your plane of your coil is kind of coming out of the board like that. Now I need to do a lot of drawing before we can actually do any analysis. So this is your coil. Remember, this normal vector N is going to stick out like this, and this is 90 degrees, so this is totally perpendicular to the plane of the coil. All right, and what I'm going to actually say, it's 90 degrees, this normal vector is indeed 90 degrees to the coil, but let me draw one more field line here to make this absolutely clear. Let's draw one more field line like this. The coil is actually, we're going to call it an angle theta with respect to the magnetic field itself. Okay, so as the coil turns, right, because this is a motor, so it is going to eventually rotate like this, right? As the coil turns, this angle changes. So as we go like this direction, this normal vector goes down, 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 down until it lines up perfectly with the magnetic field. If we continue going, then it goes this direction. And so as we go up here, the normal vector is straight up and down. So this angle basically reflects the orientation of the coil in the magnetic field, right? So yes, the angle of the normal vector to the coil is always 90 degrees, but the angle of this normal vector to the fixed magnetic field, we just label it theta. It's going to change as the coil rotates, I guess is all I'm trying to say. Okay, so what I want to show you here is that this guy, from the length of the coil, right, like this, all the way to the end, like this, we're calling it a length B. That's the sort of dimension here. And then let's briefly label the current. So right here, I want to say the current is coming out towards you, and then it's going to go down, then it's going to go into the board, then on the other side of the coil, it's going to go up. So this is kind of difficult to say. So all I'm going to do is sort of draw this with an arrow I, and then here I'm going to say I is out of board right here, and then here I'm going to say I is into board, Now, again, you have to use your imagination a little bit here. Here's the coil. It's in 3D space like this. What we're saying is the current is coming along this edge out of the board towards you. Then it turns, and then it goes down like this. Then it goes back into the board like this. Then on the other side, it's going up. So here on this side, the current's going down. On the other side of this parallel edge, the current's going back up. And of course, it's circulating. And looking back at my drawing, it's a little bit misleading the way I have it here. These arrows really, if I'm going to be totally consistent between these two views, really should be reversed. So this should go like this, this should go like this, this should go like this, and this should go like this. So if you can kind of like look at the side view of what I have here and kind of like flip this guy up and look at it on its side, then this would be coming out, this would be going down, this would be going in, which is this direction, and then it'll be going up over here. So this oblique thing is just kind of get your bearings. Really what we're going to do is the analysis based on this version here. So we're ready to really start doing some work here. If we look at each edge, right, and use the right-hand rule, remember, the force on a current-carrying wire in a magnetic field is I times L, which is the length of the wire in the direction of the current, cross with B. Okay, so what we need to do is look at those two guys. So here on this edge, we have a current going down, and so we can do the right-hand rule immediately. What we can see is that if we're looking down and we cross this guy here, like let me go ahead and put the current vector here, for instance. Here's B, here's I. If we're going to go I, L cross B, then what we're going to do is cut into this guy, crossing IL here, the length of the wire in the direction of the current flow, crossed in the B. We're going to get a force on this edge, which looking from your point of view would be this edge of this coil is going to be coming towards you out of the board. When we cross it, the force is going to be pulling it towards you. All right, now let's forget about the other sides. Look at this edge on the far side, the parallel edge. The current's gone into the board and it's kind of going up the other direction. So it's going to be exactly opposite. We're going to have, forget about this arrow here, we're going to have the current going up like this. And when we cross LIL cross B, we're going to get crossing it this direction into B, we're going to get a force into the board from the other edge on the other side. So basically, when you look at this edge here and you cross it with B, you're going to get a force out of the board. When you look at the far edge, you're going to cross the other way and you're going to get a force into the board. So what you're going to get, looking from your point of view, is the force acting on this edge is going to be towards you. The force acting on the far edge is going to be away from you. They're totally going to cancel. There's no rotation as a result of that. I mean, I can take my finger here, my finger here, pull this paper. That's all it's going to do. It's just going to stay motionless, and it's going to be equal and opposite forces pulling on the coil, but they're pulling in opposite directions, so nothing happens. So the forces that result from the current flowing in the two parallel edges, this edge and the one on the far side, totally cancel out. Nothing at all happens. No rotation, no force, no movement, no nothing. They just basically cancel out. So there are forces on those edges, but nothing happens as a result. All right. So there's only two other edges in this coil. There's this one, right, which is this edge here, and there's this one, which is this edge here. So here we have said the current is coming out of the page. Now let me go ahead and take some time to erase this because I'm going to need a little bit of room, right? Get a little bit of room here. And so this guy right here, let me put, just to make it clear, out of board. So what we have here is, on this edge, the current is coming directly out of the board. You can think about your coil. It's coming this direction. It's coming out of the board. Now, if we do IL cross B here, what we have here is, we have L coming this direction, crossing with the magnetic field B, which is this direction. So if I cut into L and I cross into B, I'm going to get a force pointed up. Right? So let me go ahead and use green for that. So what I'm going to have here is a force pointed up. All right, so let's go down to the other guy here. So we have the current coming out, it's going down the wire. Here, the current is going in, which means the current is going into the board sort of along this edge here. So I need to find IL cross B there. So if I look at this guy, again, you have to use your imagination a little bit. It's going into the board. Your magnetic field is going this way. So if I cross IL cross B, I'm going to cross IL, cross with B. I'm going to get a force pointed down. So this guy is a force pointed down. Now I think you might be able to see where I'm going here. If you put a giant pivot point right here, right, and fix that on a shaft, you can see immediately that you're going to have a force pulling this end of the coil up and a force pulling this end of the coil down. So if I have my coil here and I'm pulling up here and I'm pulling down here, it's going to cause it to rotate like this. And that's exactly really where the rotational thing comes from. So sort of the coil is going to tend to rotate this way, just like I've drawn in purple. It's going to tend to rotate. What you've really done is induced a torque, right? That's what we call torque, when you have a force that's kind of causing something to rotate. We talked about torque back in Physics 1. It's basically when you have a moment arm of some kind and a force at the end, like let's say this is a force at the end, and you're trying to pull this guy around a pivot point. So we have a pivot point, well, a fulcrum if you want to call it that. We have forces that are equal and opposite, and they're tending to try to rotate this guy through. So if there's nothing else you get from this lecture, if there's nothing else that you get beyond all the math that I'm going to do in a second, beyond the problem that I'm going to do after that, if there's nothing else that you get, what you need to understand is that if you take any coil of wire, and put it in a magnetic field like this and let the field go in this orientation, what you're going to get is a force on this side of the coil that completely cancels with the force on the other side of the coil. So these forces from this length of wire really don't contribute anything. But the force that arises from these two corresponding parts of the path tend to pull that coil in a circle, basically, tend to rotate it. Now also notice that as we rotate it, this normal vector n rotates with the coil, so that's a nice and convenient way to sort of characterize which direction the coil is going. And that's something that we'll talk about a little bit more in just a second. All right, so now that we know conceptually what's going to happen, we know that we're going to get a torque. What we want to do is calculate what that basically is. Ultimately, what we want to do is calculate what that torque is. Much like when we have a wire in a magnetic field, we want to know what the force is on that wire, pushing it in a certain direction. We put a coil in a magnetic field. We know it's not going to be sliding around left and right. We know it's going to tend to rotate. We want to know what that torque is going to be, and we want to find a formula for that. So that's what we're going to basically do now. This is conceptual. Now we're going to move a little bit into math. Now, don't forget that the force on any one of these lengths of wire, which these are the only two we care about, this length of wire here and this length of wire here, the force is going to be I times the length of the wire L times the magnetic field strength B. Now usually it's ILB times the sine of theta, but when you think about it, since this wire is here and magnetic field's here, they're perpendicular. Since this wire is here and magnetic field's here, the way I've drawn it, everything's perpendicular. So sine of 90 degrees is 1. So you don't need to put sine of anything here the way I've drawn it. And that's the way you would construct a motor in the same orientation as well. So what you have is the force, basically. This force here is I times L times B, where L is the length of the wire here. And this one is also I times L times B. And we've drawn the orientation of F based on the right-hand rule. We've already done that. But in our particular problem, L is not something we're really using. We're saying that the length of this edge is A, the length of this edge is A. So let's just replace L with A. Not rocket science there, that's all we're doing. We don't need the sine of anything because they're already perpendicular. This wire length is already perpendicular to the field. Okay, so this is the force acting on this edge. So this is a piece of wire here on this edge. The force acting on this guy is given by I times the length of this guy times the magnetic field that we're immersed in. Now dig back into Physics 1 and you should remember the torque on a current loop. The torque, I shouldn't say the torque on a current loop, the torque on anything. The torque on anything, usually when you talk about torque, you have a moment arm, right, which is basically the length of whatever it is connected to the pivot point, in this case my shoulder, and you have a force acting at the end of that guy. Think about a wrench, okay? You know, wrenches, we all know, are really good at loosening nuts, right, because they give us mechanical advantage. The reason they do that is because you hook it onto the nut and you have a very long moment arm. You're exerting a torque that's kind of multiplying your effort, so to speak, and letting you kind of get leverage on that guy. So the farther that moment arm is, the more torque you know that you have. If you have a wrench, you know, this long, you're going to be able to really, you know, loosen some big nuts because you've basically got a lot of torque. So the torque in general terms of anything is denoted by tau, like that, torque. And it's equal to R cross with F. So this is the moment arm, the vector that represents, the length of whatever moment arm you have, in this case from my shoulder to into my arm. And then you have the force vector. So I may have a force, like this pin here might be a force right at the end of my arm. Maybe I'm angling the force this way. Maybe I'm angling the force like this. Maybe I'm angling the force like this. In all of these cases, because I'm changing how the force is angled with respect to my moment arm, the torque is going to be different. Obviously, if I angle the force directly out of my arm, then I'm not going to rotate anything. So I'm going to have no torque. But if I take this force, like a wrench, and if I try to angle the force at 90 degrees to my arm, then I'm going to have nice maximum torque. So that's why it's a cross product, because cross products are RF times sine of theta. In fact, that's what we're going to write down next. The torque is R times F times the sine of the angle between these two things. All right, between these two things. So now what we want to do is apply the general idea of torque on anything to this situation, because this is mechanics at this point. We've left the realm of electricity and magnetism. We're back to physics 1. We have a moment arm. We know the length of it, we have a force, we have an angle. Let's just put it into the torque formula, and that's all we're really going to do. Now let me ask you this, what is the moment arm? Well, this is the pivot point, so this guy here, this length from the pivot point to the place where we put the force itself, the action point, so to speak, that is R. That is the length of the effort arm, or whatever we're trying to do. So since I labeled this entire length B, the length of the coil, the distance from the pivot point to the force point is B over 2. So it's B, we'll do it like this, B over 2, all right? B over 2. This is R, so this is R right here. Now we need to do F sine theta, all right? So let's do that. So what we'll have here, for the force, we already know what this is, I times A times big B. Don't forget big B and little b. Little b is the length of the loop, basically, on that edge. Big B is actually the magnetic field strength. The force here, we just calculated here, we put it in here, times sine of theta. This really is the torque acting on this guy, at least due to this force right here. So what we've done here is looked at the torque due to this one here, but don't forget we have an equal and opposite force pulling in the other direction. So we have to add to that is the torque due to the other one, which is also going to be B over 2 times I times A times capital B times sine of theta. Make sure you understand that, because basically this force is causing a torque to rotate in this direction. This force is also causing a torque to act in the same direction, so you add them together. The torque due to the first one is this. We already justified that from this guy. The torque on the second guy is exactly the same because it's the same force. It's the same action arm here, basically. Everything's the same. It's just pointing up, which is generating a torque in the same direction. Now, just to make absolutely sure that you're convinced that this is right, I want to take just a minute. Let me erase this for a second. I want to take just a minute just to sort of prove it to you. So let me do this in purple. Let me extend my action arm out a little bit here, like this, right? Now, would you agree that if I have a force acting like this, then this force like this can be split up as follows? So I could have this guy here, this perpendicular force, this force perpendicular to my action arm is really what I care about. So if this angle is theta up here, that's exactly the same as this angle here, theta down here. And that would mean that this guy, this one right here, would be F times the sine of theta. F times the sine of theta. That would be the force acting perpendicular like this. When you have torque, the formula, the equation that you learn in physics 1 is R cross F, which is R times F times sine of theta. This is why it works, because when you calculate a torque, really, all you care about is the component of the force that acts perpendicular to your moment arm. Much like a wrench. Think about a wrench. If this is a nut here, and I have a wrench and I'm trying to loosen the thing, it doesn't help me if I'm pulling along the line of my wrench. That doesn't generate any torque. The only thing that we really care about when we're loosening nuts and bolts is how much force we can actually act perpendicular to this wrench, right? So if I'm pushing exactly up with respect to my wrench, I'm going to get maximum torque. Now, if I do something in the middle, if I kind of angle my arm like this, where it's not a clean 90-degree angle and I'm pushing at an angle, what you're doing when you calculate this cross product is you're finding what component of my force of my arm actually does act perpendicular. And you're finding that component that acts perpendicular to my wrench. That's what we're using when we multiply. That's why it's RF sine theta, because the sine theta is taking the component of this force that's acting perpendicular to your action arm. That's all we're doing here. You have an action arm, you have a force. This F sine theta is just looking at the component of the force that's going to tend to turn this thing. And that's why it's done this way. All right, let me finish this up. So what we have, since we have basically the same terms everywhere, the torque on this current loop, B over 2 plus B over 2 is going to give you B. So what you're basically going to have is I times little a times little b times big B times sine of theta. This is just adding this term to this term. B over 2 plus B over 2 is going to give you B. Now, this is the answer. This is the torque on a current loop. So what we've basically shown is if you take a loop, you put it in a magnetic field and orient it this way, if you take the current in that loop times the length of one of the edges times the length of the other edge times the magnetic field strength B, and multiply it by the sine of this angle. So in other words, it's going to depend upon the angle of this coil, basically. Then you're going to get the torque on that current loop. So in this case, you can see that the torque basically does depend on what angle the coil is oriented in. If we turn the coil like this, so that the normal vector is pointed out, then the angle between the normal vector and the magnetic field would be 0. So sine of 0 would be 0, so the torque would be 0. So if the coil is lined up like this, the torque is 0, nothing will happen. If the coil is angled this way, where the angle between the normal vector and the magnetic field is 90 degrees, we're going to get a maximum torque. So you can see the torque on the coil depends on how the coil is pointed, basically. If it's pointed where the normal vector is lined up with the magnetic field, you're not going to get any torque. If the normal vector is pointed 90 degrees to the magnetic field, you're going to get maximum torque. So another way to phrase this is sort of like one of the major conclusions of this section is this normal vector here that we've drawn in all of these diagrams, it always tends to rotate, the forces always tend to rotate the coil to line up that normal vector with your field. In other words, no matter how you put a coil in here, if you draw a normal vector, right? If you draw a normal vector in the orientation that I've drawn it, then the forces are going to always tend to rotate this coil to line up this normal vector with your magnetic field. That's always going to be the way it is. No matter if you're here, no matter if you're down below, whatever orientation you're at, it's always going to tend to rotate it to be able to bring in alignment with your magnetic field. And by the way, to generate the normal vector, if you have a loop like this, you take your right hand and you go in the direction of the current flow, and that is the direction of the normal vector in. And that's exactly how I have it drawn right there. So that's why we have in oriented up like this. Okay, now, this is the torque on a single current loop. In a magnet, you can multiply, in a motor I should say, you can multiply this effect by putting lots of turns. So this was for one turn. We only calculated for one turn. If you have 50 turns or 100 turns, you can multiply the torque, right? So you can get a motor to be more powerful or turn faster or whatever it is you're trying to do. So for multiple turns, you can have the torque is equal to N being the number of turns, times I times A times little b times big B times sine of theta. And that's a useful thing if you're dealing with multiple turns. And you can also say this is equal to times N times I times big A, I'll tell you what that is in a second, times B sine theta. Notice in this case I have A times B. When I look back at my diagram, A times B, that's the surface area of the coil, basically, surface area of the coil. So if you want to, you can rewrite, instead of A times B, you can rewrite that as product, which is the surface area of the coil. So this would be number of turns times the current in the coil times the surface area of the coil, if you were to kind of look at it from a top view, calculate the surface area, times the magnetic field times the angle that the coil is with respect to the field. This is nice for a number of reasons. I'm not going to prove this to you here, but I'll just tell you that we've derived this whole thing for a rectangular coil. All right, we've derived the whole thing with our sides and everything with a rectangular coil. It can be proven that this equation actually holds no matter what the shape of your coil is, no matter what the shape of your coil is. If it could be a circular coil, right? In that case, you wouldn't really be able to apply A times B very easily because it's a circle. What if you have an egg-shaped coil? What if you have a triangle-shaped coil or something? It would be difficult to apply this guy because we derived it in terms of our rectangle here. But here, this is just saying everything in parentheses is really properties of the coil itself. The number of turns, the current in the coil, and the surface area of the coil. They all depend on, no matter what geometric shape you have, you can figure this stuff out. So it's good if you have an egg-shaped coil or a circle-shaped coil or something like that. And then you have, of course, B times sine theta, which is representative of everything outside of the field. So I think I've covered everything here. What I'd like to do is go ahead and work a quick problem to show you how to sort of use this. This by itself is a great thing to know how to derive because you might be asked on your test, and even if you're not, you're going to have a deeper understanding of torque on a current loop. So it's a good thing to do, and I'll come back and summarize it in just a second when we get done with this problem to kind of make sure that it's, you know, it's doing nicely up here in your head. So let's go and work a quick problem. Our problem says a 2-meter long wire loop carries a 2 amp current in the shape of an equilateral triangle. If the loop is placed in a constant magnetic field of 0.5 teslas, what is the maximum torque that acts on it? The maximum torque. That's a huge keyword. So we have a coil, we have a current loop in a magnetic field, but it's not a rectangle like we were doing here, it's a triangle. This is a great example of when you would want to use the bottom formula because triangle is totally different than what we've been deriving it in terms of. And we also want to know what's the maximum torque. So basically what this means is, if you have some kind of magnetic field like this, and I'll just kind of draw a little sketch real quick, you know, then basically you want to orient, if you want to look at the maximum torque, and it's an equilateral triangle, I'm doing my best to kind of draw it. What you want to do is orient your thing so that your normal vector is coming straight up, so that the angle between your normal vector and the field is 90 degrees. Because I already told you in the last section that no matter what shape coil you have, when you put current through it, this normal vector is going to want to rotate the coil to be lined up with the magnetic field. So maximum torque is going to happen in this orientation when you have 90 degrees between here and here. That's going to be when the torque is maximum, trying to push it over. All right, so what we're going to do is we're going to use this equation down here, NIA V sine theta, to find the maximum torque. So the torque is N times I times A times B times the sine of theta. So what we have here is the torque on this current loop is basically going to be the number of turns in the loop, which in this case is just 1 because we only have one actual loop here. We're not doubling up over and over and over again, according to the problem, times the current in the loop, which we know. The surface area of the loop is really the only thing we don't know. We do know the magnetic field strength. We do know what sine theta is because the problem was asking us for the maximum torque. The maximum torque is always going to occur when this coil is oriented so that the normal vector is 90 degrees to the magnetic field. Immediately when we switch the current on, it's going to tend to rotate the entire coil this direction until it lines up with the magnetic field there. And then the torque will be a minimum once the coil is oriented this direction. All right, so really all we need to do is find the surface area of this coil. So what we have over to the side here is we have an equilateral triangle, and I'll do my best to draw an equilateral triangle. All right, so if you remember, the surface area of a triangle is 1/2 times the base times the height. Of course, this is the base, like this guy right here, but the height is actually this distance here. So we need to figure out what that is. Now, according to the problem says we have a 2-meter long wire loop. That's all it tells us. But it's a huge clue that we know it's 2 meters long because that means that each one of these sides is going to be 2 divided by 3 sides is 2/3 of a meter. Since we have a 2-meter long current loop, that means that this side is 2/3 of a meter, this side is 2/3 of a meter, and this whole bottom side is 2/3 of a meter. So the area of this is going to be 1/2 times the base is 2/3, times the height. The height I do not know from this drawing. So you need to basically take a moment and figure out what the height is here. And we'll call it h, right? So if you were going to look at this guy, this is a kind of a right triangle on the inside of here. And so what you're going to have is, with the Pythagorean theorem, you're going to have this side, right, which is 2/3 divided by 2, is going to give you 1/3. So you're going to have 1/3 squared plus the height squared, this guy, is equal to 2/3 squared. That's just Pythagorean theorem. This guy squared plus this guy squared is equal to this guy squared. All right, so what you're going to have is 1/3 squared is 1/9 plus h squared is equal to this guy squared is going to be 4/9. So h squared, when we subtract this guy over, 4 minus 1 gives us 3, so we'll have 3/9. So if we solve for the height here, we're going to take the square root of both sides. The height of the triangle is take the square root of the top, you're going to get square root of 3, square root of the bottom, square root of 9 is 3. So the height of this triangle is square root of 3 over 9. Square root of 3 over 9. So let me take this information and kind of feed it back up into this other calculation to find the surface area. The surface area of this guy is 1/2 times the base of this whole equilateral triangle, which is 2/3, times the height of this equilateral triangle, which we just found, square root of 3 over 3. Square root of 3 over 3. Okay, so then we can do some cancellations. The 2 is going to go out with the 2, and what you're going to have is the area is going to equal to square root of 3 over 3 times 3 gives us 9. So the area is the square root of 3 over 9. All right, so we have everything we need. Let's go ahead and take this, and we'll basically put it into this guy. So the torque on this guy is going to equal the number of turns. In the problem, it only really said there was 1 turn, so we're going to have 1. The current that was given in the problem, the current is going to be 2 amps. We'll have 2 there, right? Times the surface area. The surface area we just found was the square root of 3 over 9 times the magnetic field B. If you look at the magnetic field, it was 0.5 Tesla. Let's write it as 1/2 since we're a lot of fractions here, times the sine of the angle. So the sine of the angle that we're putting in here is 90 degrees. We already know that because we want maximum torque. So what we're going to have is this 2 is going to go out with this 2. Sine of 90 degrees is 1. So what we're going to have is the torque on this current loop is going to be square root of 3 over 9. Square root of 3 over 9. And when you actually put that into a calculator, if you prefer, you can write that as 0.193. And the unit of torque, you can look it up. In fact, from Physics 1 is Newton meters. And that's because it's R cross F, or R cross O, force times a distance, basically. So that is the torque on this guy. Now, just kind of going back through the problem. We already derived what the torque on a current loop is, right? We already talked about that. We talked about the fact that we derived it in terms of the lengths of the rectangle, but in fact it's the area that's the most important thing. And it can be proven that you don't have to have it in the form of a rectangle for it to work. You just need to know the surface area of the coil. So because we knew it was an equilateral triangle, we just did this work over here to find out what the height of this triangle was so that we could calculate its area, so that we could put the area, which we found here, into the calculation. The number of turns is 1 because we just said it was a single coil of wire. This was the current, this was the area, this was the magnetic field, and we have 90 degrees because the problem says what is the maximum torque that occurs. So you need to know physics-wise what we've learned. We've learned essentially that when we have these coils, we can define a normal vector to it, and the normal vector, the torque is going to always try to point that normal vector in the direction of the field. The torque is going to be maximum when it's 90 degrees out from the field, and it's going to be minimum when we have the guy directly lining up. So that's basically all I have as far as material in this section. You know, motors and how they work are just so prevalent and so important. And I really wanted to take some time to kind of walk through it with you here. And I want to do that just briefly, really quickly here. We have a coil we already talked about in the magnetic field. We define a normal vector N that has an angle theta to the magnetic field. And what we figured out by using the right-hand rule is that the force coming out of this side and the opposite side of the coil totally cancels, equal in opposite directions. The force coming off of this guy tends to pull the coil up, and the force coming out of this guy tends to pull it down, so we get a torque. Now, those of you guys and girls who are astute, maybe, and it's not quite so obvious at first, so don't worry about it if you don't pick up on it. You might have noticed that there's a little bit of a weird thing here. You know, we think about motors as something that we turn the current on and they go and they go and they go, and they never stop until we turn the current off. But the way I've drawn it here, if you have your coil here, you can see that the torque is maximum when we have a normal vector 90 degrees to the field, and it causes the coil to rotate. So the torque is going down, down, down as you rotate the coil, because here's the torque here. As the angle gets smaller, when the angle eventually reaches zero, in other words, when this guy lines up with the magnetic field, there's no more torque anymore. There's no more torque anymore. So how can that be? If there's no more torque, no more turning function, right? When we line up with the magnetic field, then how do the motors keep going and going and going? Well, if you actually cut apart a real motor, you'll see that it's not quite constructed in the simplistic way we've drawn on the board. In fact, the way it actually works is, see, this is the direction of the current flow here. In real motors, there's a mechanical sort of switch in there that basically, once it lines up with the field, it kind of switches the contacts internally that switches the battery current to go in the other direction once we get into this point. And so then everything reverses, and it continues to pull the magnet around, or the coil around the other way. So in other words, in real electric motors, there's a device inside the motor that every half turn that motor goes around, it's contacts inside of the thing that get reversed, and it sends the current around in an opposite direction, basically. So you can see at this point, basically, once we line up here, if we didn't do anything at all, we would have the force coming up here, and then we would have the force pulling down here, and it would just kind of tend to, boing, just kind of stay up like that. But what happens is, once it goes here, inertia kind of carries it through a little bit, and what happens is the current flow changes direction so that this force no longer points up, it pulls it down, and this force no longer pulls it down, it pulls it up. So once inertia carries it past the center line briefly, the current switches direction and the torque changes. Well, the torque is still the same direction, but the force up here pulls this edge down, and the force here pulls this edge up. So the force is reverse direction. And when we get back to this orientation, everything flips again, and so it goes and goes and goes. So every half turn, the current switches direction in the coil, I guess is what I'm trying to say. So every half turn, this force, once we get over here, it pulls it down, and then when it gets back on this side, it pulls it up, or when it gets over here, it pulls it down. So the forces keep alternating directions every single half second. So every one of those little electric motors that you see in a kit or whatever, you hook up a battery to it, it doesn't look quite so complicated, but inside of there, those coils, there are contacts that are switching the direction of the current every single half turn, and that's the only way the coil will continue to rotate, because from the physics, everything stops once you line up with the magnetic field. There's no more torque. So you must continue to alternate the guy, otherwise the forces will just sort of like even out and nothing will begin or continue moving anymore. So that's kind of the final thing I really wanted to point out to you. We have the torque here, we put it in terms of this, we put it in terms of the surface area of the coil. The normal vector likes to line up with the magnetic field, and of course in a real motor, the device in there changes the direction of the current, which changes the directions of the forces. So that's probably the best application of force on a wire in a magnetic field that we all have experience with. Make sure you understand how this is derived, make sure you understand how to use the equations, and so that way when you get on your exams, you'll understand what they're doing, you'll have good practice with it, and you won't be struggling so much because you'll have a good foundation in torque on a current loop.